Okay. Previously, right, we talked about the graph. We talked about from when you just pull the spring. Okay, when you pull the mass from this position, the initial position x naught, the bow x. When you pull it to this position, bow x1. Okay, and when you release, we study the movement from this portion when you just release to this portion. Okay, so now we talk about the motion when it springs back to this position over here. Okay, so in a graphical way, what we are analyzing now is this. Okay, when you just previously we were analyzing from this point, and then when you release, it starts to go to this point, which is at this position over here, x0, right? And then now it goes to x2, and then it goes to x2. In this video, and in the this series of the video, whatever that I'm talking now, okay, I'm talking about what I'm gonna talk now is from this position when it springs back, okay, to x0, and then to x1, perhaps lesser than x1, but however, we're gonna know how it's gonna move. So this is the portion that we're gonna talk about, okay, when it springs back to this position. This is one cycle. So just to take note, this is pi, and this is 2 pi, and this is 1 period, okay, 1 period. So we're taking only, previously is half cycle, now we talk about another half cycle, okay. And then along the way, I want to make sure that you understand uh, another thing about the k constant, the convention sign of the k, which I didn't explain earlier just now. So let me again explain the whole system. As I say, we're analyzing from this point and then springs back to this point. Okay, perhaps lesser than x position x1, but however, that's the free the body diagram. We know the convention is still the same. This in this direction towards the right is plus VE. Now we're talking about analyzing from left to right. Okay, previously was where are we? Previously was right to left, correct? Previously was from right to left. Okay, now we from springs back to left, from left to right. So therefore, when you just release the mass at x1, okay, I would want to make this very clear. At x1 position, which is sorry, x2. Okay, sorry, this is x2. At this point, when it kind of springs back, maybe hold on a while. Okay, yeah, when it springs back at x2, okay, from x2, okay, from x2 to x1. One key thing that I realized is that currently, apparently, the k, the stiffness k of the spring itself also takes into account with the convention. So what I mean is that previously, in the previous past video, we talked about minus kx, right? It's just saying that the convention, if you are moving in this direction, um, this is plus. If you are moving in this direction, this is minus. This is partially correct. Okay, what I mean is that, okay, the x itself, where I would say that this is x1. Okay, this is x1. When you move back here, okay, I'm talking about just now that video, previous video. So when you move back x1, okay, typically yes, it's negative, but however the k constant, there is a certain spring force, okay, spring force that is trying to resist the motion going in this direction. So the spring force k, okay, this is the spring force k is actually plus. So plus multiplied by minus is minus kx1. So if you visualize that the spring, when you start to release, the force is pushing towards this direction, right? The force is pushing towards this direction, correct? So the force is pushing this direction. The spring itself has a reaction force trying to resist the force that is trying to push back, right? Yeah, this is by far my best explanation. Although it may not sound that right, but you give me a minute a while. Yeah, it should be correct, and it must be correct because whatever thing that the law of conservation says that whatever goes in must come out. Okay, so whatever force pushes the spring must push back the same reaction force. So therefore the reaction force K itself is going towards positive. So therefore K is equals to positive, while the x1 is moving towards the negative side. So this is why negative kx1. Okay, so with this, hope I make things clear. You have to visualize, this is very important because yeah, if you want to derive certain stuff, you need to really understand the physics behind things. So apparently, yeah, this is how I believe that is how it is being done. So let's continue. So for this case, now we are gonna spring back, okay, from position x2, the bow x2 to x1. So when it springs back up to this, when it springs back up, there is your force is going in this direction, right? There is a force going in towards this direction because you want to spring back out, right? So the spring itself wants to resist the force that is going to spring back. Okay, so the spring itself is trying to resist the force that is going to spring back. So therefore, the spring itself, the spring reaction force is actually this minus k. Okay, while the x2 itself, because it's moving towards the positive side, so it's plus VE. So it's moving in this direction, is alright, perfectly fine. So however, since negative k multiplied by x, there will be it will become negative kx. So we have negative kx2, okay, because yeah. And then there's as easy, it's pretty easy that the friction force is just opposite the movement of the thing. So when you're moving this, the friction is opposite. So it's just this. And then we can set up an equation. Yeah. You give me a minute a while. Okay. So after I written down quite a lot of things. Anyway, so now since we know the relationship, we can just plot an equation. So it's just minus f minus kx 2 equals to mx 2, okay? It's the same thing as the previous equation. If you want to, argue that, dude, it's the different, okay, it's the same trend, just that this one is minus, okay? And then we rearrange again. Similarly, we rearrange, and we get this equation, and then we solve using the second order d differential equation. This is the complementary function, and this is the particular integral. And then we know that to solve for particular integral, you have to first divide everything by m again. Similarly, we do the same thing also. We have this thing, the general equation, and then we solve for particular integral. We also divide by m, and then the same thing. So yeah, we do similarly the same step. So the only way is to solve using binomial, as we explained earlier, why we cannot solve using the typical differential equation method for the particular integral, because we will make the equation more hairier, and you have no any final answer for that. And then we rearrange the equation into binomial type of equation, which is the x plus 1 to the power of n, if you remember, is this form. So that such that after we have this one, we can actually plot out a series in accordance to x and n. Yeah, I'm very tired, so this is why my mouth cannot speak properly. Yeah, and then you rearrange, you use the d operator. Okay, yeah, this is the operator over here. Once you use the operator, you solve for binomial theorem, and then you eventually get minus f over k. This is your particular integral. And then one thing I need you to actually take note that for the if you were to still how do I say it? Okay, so apparently it's just as you can see it's the constant k. Okay, it's the constant k. It's this dude over here. So okay, if you don't know what I mean is that you still remember back the trail function or the particular integral when it's just any constant you put in any constant, and then if it's cosine, if it's non-homogeneous, right? Yeah, if it's not non-homogeneous, this portion here, if it's like cosine, then you have to sub in it as cosine and sine, and then you differentiate two types and you sub back into the equation here, and then you solve for the constants, the coefficient, and then yeah, happy. So yeah, imagine. So apparently you can see that this dude over here minus f over k and previously the f over k. Um, okay, the f over k is the same thing as this. It's just that it's divided by k only. That's all. Okay, it's just a constant. It's still a constant value. Okay, and therefore and don't be complicated by my k and this k. My k and this k is totally different case. Okay, so it's just let you know the convention is using k lah. Never mind. But I just want to let you know the idea behind it, and also that particular integral still takes on the form, that particular form, rather than suddenly become cosine and sine, which is totally, messed up. So with this said, I haven't end. This video haven't end yet. So I mean this series haven't end yet. So apparently the next video I'll just continue with. Since we didn't know the particular integral, we have to solve for our solution for a1 and b1 if you remember. Our a2 and b2, sorry. So it's a2 and b2. So we have to solve for this, and then we have to do a little comparison plus minus, and then we'll get our answer. So see you in next video.